Okay, so I don't remember what I told you at the end of the lecture on Thursday if regarding the computer exercise. Did I say that we should do it today or next lecture? I don't remember. I didn't say anything, okay. So let me start with the next topic today and in the first hour, and then let's see how long it takes to get to the end, and then I think I can start the exercise either today or Thursday, depending on the time that we take today. Today we have a relatively limited topic to discuss, but it is again a little bit demanding in terms of notations, and therefore I just want to make sure that I dedicate enough time to it. Just 1 second, I just move a little bit the camera here. Yeah, I think this should be fine. So let me just dim the light a little bit. Good. And let me move to the website. What are we going to talk about today? It's groundwater models, and I want to give you just a brief introduction to the context. We are discussing deductive methods for assessing water resources availability. And if you remember, when we discussed about the inductive methods, we said that we talked about time series analysis, basically flow duration curves. And for groundwater, we just made a brief introduction. We said that we can get the data to analyze in order to develop our inductive assessment. We can get data by testing, by aquifer testing, data through wells. And I said that these are the data that we can use for inductive assessment. We didn't talk about specific methods because for groundwater assessment, the techniques for inductive reasoning are less consolidated than the techniques for surface water, for this very simple reason that there is, for surface water, we have a systematic monitoring that started a lot of time ago. We have long time series. With groundwater models, the data are more sparse, the situation is also different with respect to surface water, because for surface water, the domain, the catchment, which is the collector of surface waters, is very well defined and can be very well identified with simple reasoning by following the divide. For groundwater bodies, the geometric characterization is much more difficult. They may be displaced at several levels in the underground. So in the same region, we may have several aquifers that are displaced in different ways in space and also in terms of depth. And therefore, from a geometric point of view, it's more difficult to define these bodies, while for surface water, it's much easier. And this is why monitoring started relatively later, monitoring of groundwater, because at the beginning, when surface water started, we didn't have a clear perception of the extension of groundwater bodies and their value also. So the situation is that data availability is much sparser, and the methods for inductive assessment are based usually on analysis of a single well or group of wells with techniques that are in a way devised ad hoc, depending on data availability and depending on the specific needs. But I anticipated when we discussed inductive method that I will focus on deductive methods with a little bit more emphasis. And this is what I am doing today. When we passed to deductive methods, we again started with surface water, and then we took into consideration Imodraeforanov modeling. We talked about the rational formula, the linear reservoir, and IMOD. Now today we are introducing groundwater models. We need to understand how they work, what are the principles. You can understand that it's again a problem of a fluid that is moving. So the principles will be the same as for surface water. Conservation of mass, first of all, and conservation of momentum energy, because it's a physical problem, first of all. Then we can also identify water quality problems, which means also involvement of chemistry, but at the beginning it's a physical problem. So let's understand how these physical laws are applied to groundwater bodies. We understood how they are applied to the surface water. We refer to a domain, to a spatial domain that is the catchment, and we apply this conservation equation at the catchment level, basically, with different techniques. Now, let's see today how to apply these conservation equations to a groundwater body. And I will need to introduce some articulated notation. We will not go into the details of specific models. I will explain you why. So what I am interested in is that you understand the concepts, and their application will not be discussed in detail here. The reason is that their application is not so easy as for surface water, and therefore it's usually dealt with in dedicated courses, which are also available here for your degree program. So I will provide an introduction, but I will not go into the details of the application again, because this would take too much time. But still, in order to provide the introduction, I need to introduce a little bit complicated notation, and I just wanted to anticipate this to you because you know, they are differential equations, and therefore the notation is a little bit difficult. But the concept behind it, it's not difficult. So I really would like, and I invite you to focus on the concept. And then if you understand the concept, also the notation will become clear. I refer to the PowerPoint presentation. What you see on the screen now is my usual web page, Deductive Assessment. And the last part is devoted to groundwater models. And let me just move to the presentation, but before moving to the presentation, let me take a step back and show you a figure which clarifies a little bit the problem. So let me go back a little bit in one of my previous lectures, which is sustainable management of water resources. And let me just go down here to this figure, which shows the typical structure of an aquifer. One second, I am trying to increase it. Okay, good. So this is the typical structure of an aquifer. An aquifer, first of all, it's a body, it's a water body, whose extension in principle is not known. We can identify the extension with prospections. And we drill the soil, and then we try to understand by measuring the water level, measuring also taking soil samples, we can understand what is the extension. It's not so easy to define this picture in the details, but what is important again is to get the concept. Usually we have a part of soil that is not saturated, in where it's called the unsaturated zone. And keep in mind that the unsaturated zone is usually divided in two layers. One layer is dry, another layer is humid, and this humid layer is called in English the Vaduz zone. But and then if you go more in depth, you finally get to water, okay? And the divide between the saturated part and the unsaturated part is the water table. It's a called water table, which is the surface water level, okay? And usually this first aquifer that you find in the underground, if the soil is permeable, it's unconfined, which means that you don't have above the water table impervious layer, a limited permeability layer that in a way protects the aquifer and keep the aquifer under pressure. The water is free to go up. If the water pressure increases, the water table goes up, typically for the effect of infiltration through the permeable soil. And the fact that the aquifer is unconfined means that at the water table, the pressure is atmospheric pressure. Okay, it's a free water surface. It's in the soil, but still it's free. And air can get into the soil and push the water down if the atmospheric pressure is higher than the pressure of water. So at the water table, you have the atmospheric pressure. This means that the aquifer is not protected. If you infiltrate oil, if you infiltrate any other pollutant, then the aquifer can be polluted, can become polluted. You understand that it is a problem, because it is a problem anyway when water gets polluted. But you understand that if you get polluted a river, it's a critical situation, but it's less critical than getting an aquifer polluted, because to clean a river is easier than to clean an aquifer. To clean a river, you flush water, you allow water flushing, you just stop the pollution, you stop the emission of pollutants, and then you let the river flushing. The river is quite fast. The velocity of water into the river is quite rapid. In the underground, let the water flushing, it's a problem because the velocity is very slow. And therefore, in order to purify the soil, you need to wait a very long time. Okay? Very good. And then when you go in depth, usually you find an impermeable, a rocky layer, a layer with limited permeability. It is what keeps the aquifer close to the surface. Of course, if the rocky layer is very deep, then the aquifer becomes very deep. If the rocky layer is close to the surface, of course, you have the bottom there, the bottom of your aquifer. But then typically, below the rocky layer, you have another section which is permeable with high permeability. And therefore, it means that there is porosity there. And then you find very often water there. And you may ask, how could the water get there? For many reasons. It can be trapped there after tectonic movements, and it's called usually fossil water in this case because it's very old, or it may come through infiltration from the mountains. It's not depicted in this figure, but you may have a flux of water in the deep underground, in the permeable layer, which is confined by the impervious layer above. You can have infiltration from the sides. Okay, it's not depicted here, but you can have infiltration. And also you may have some infiltration through the rocky layer, because even if it's limited permeability, you may have cracks, fissures, and you may have some infiltration, which puts the confined aquifer under pressure. Why we say under pressure? Because if you assume to remove the rocky layer, what are you expecting? That this water comes up, because it's water that is under pressure. In fact, we divide the wells in phreatic wells, which get water from the unconfined aquifer, and the so-called artesian wells, which take the water from the confined aquifer. And the artesian wells, in some cases, are very interesting because water may come to the surface spontaneously without pumping, thanks to the effect of the pressure. Yeah?
In some article, I read that if upper layer permeability is lower than 10% of down layer, the upper layer is the unconfined aquifer. Is it true or not about the 10%, lower than 10% or not?
I mean, it depends. It depends on the context. I wouldn't say that this is a general law, but of course, if you have an aquifer, if you have two aquifers superimposed each other, and the aquifer the lower aquifer has a lower permeability, then it can become indeed a confined aquifer, because the lower permeability basically makes the infiltration of water slower, but the result is that also the exfiltration of water is lower. So if you think to two sponges, one that is very permeable and the lower one that is less permeable, and you put the water in the upper one, then you have, after a while, the lower sponge that becomes wet. And then if you dry the upper one, it gets immediately dry. The lower sponge becomes humid, remains humid. And what is the result? That you have an internal pressure in the lower sponge that is higher than the pressure in the upper sponge. And then you may get a very slow upward movement of water from the lower sponge, which has higher pressure, internal pressure, to the upper sponge. And so this is a particular situation that is more complicated to understand. I prefer this type of figure because it's clear that you have two different aquifers separated by a kind of layer that is not permeable. And I think the situation is easier to understand in this case. The only thing that is missing here is that you don't see the possibility to have infiltration in the confined aquifer from the sides. You don't see it here. Actually, here it looks like you have only infiltration through the reduced permeability layer. So how can we study this complicated situation? I mean, aquifers are highly heterogeneous, because you can understand that soil properties change from one place to another and also change along the depth. Okay, so indeed they are very heterogeneous. It's not appropriate to study them with a lumped approach. So with the surface water, the water bodies are treated with a lumped approach. They are treated as a unique entity. You can do it. We did it with IMOD, with the linear reservoir. With the linear reservoir, we assimilated the surface water body to a tank. In this case, this is not really appropriate, because you have a much more important spatial variability along the three directions of space. So what is the approach that we usually adopted? That we study the movement at a very local level by discretizing the body in several elements with very low dimension. Okay, so basically we have to study the aquifer by discretizing the spatial domain in elements with infinitesimal dimension. Why? Because if the dimension of the element is infinitesimal, is very, very tiny, we can assume that the element is homogeneous. This is a classical approach in physics to model heterogeneity. You study the body, the system at the local level. You split the system in infinite elements with infinitesimal dimension. So you split the control volume in infinite elements with infinitesimal dimensions. And in this way, you can assume that each element is homogeneous. On the other hand, you understand that this is complicated. If you apply conservation equation instead of once, infinite times, then you get a more complicated approach, because you have also to put these elements together, and you have to make sure that you take into account the fluxes of water from one element to the neighboring ones. And the result is that you have to use differential equations, because when you study at the level of infinitesimal dimension, you can describe changes from one element to another through differential equations. Which, I mean, we hate a little bit, we don't like them, because differential equations don't describe the variables of interest, describe only the changes of the variables. And then in order to get an explicit representation of the variables, we need to make an integration. But you don't have to be concerned by differential equation and integration, because differential equations just describe differences, and we learned how to make a difference at the primary school. And the integral is nothing else than a sum, and we learned to make additions at the primary school. And why are the integrals and the differential equations so nasty? Because if you want to treat them analytically, it's complicated. But through numerical integration and numerical handling, they are just differences and sums. I think I already made this consideration to you. So you don't have really to be concerned. The only thing is that, of course, you have several equations now coming together, and a notation that is a little bit more articulated, but you don't have to be concerned. But I just wanted to give this introduction to clarify that I have to work at the very local level. So the first thing that I have to make is to define what we call the control volume. So the volume with respect to which we apply the conservation equation, conservation of mass, conservation of energy or momentum, okay? If you're not familiar with conservation of momentum, just take into account that momentum is a vector and the energy is a scalar, and they are very, very close. They are equivalent. But one is expressed in vectorial form and the other one is scalar form. Okay, now let me just close this and let me show you this figure, because I think this solves the problem of explaining how the aquifer gets under pressure. What you see here is only a confined aquifer. Okay, which the orange layers are reduced permeability. And why it is circular? Because it's the result of a tectonic movement. If you think the tectonic movement that raised the mountains, then you get elevated portion of the Earth's crust and lower portions. The lower portions are the valleys, etc. And you can understand that if you have infiltration from the mountains through the through the permeable layer, which is carved, then when you get on the valley bottom, the water is under pressure, because you have the weight of the water up here on the left and the right that pushes the water that is in the valley bottoms against the upper layer. And if you put a well in the upper layer, what happens is that you may get water springing at the surface. Why? Because for the principles of the communicating pots, you know, I don't know if it is the correct word in English, but you see where is the level of the water on the left and on the right. You get water out from the wells at the same level because of the pressure. So you understand why the aquifer is under pressure here and where infiltration comes from. Be careful. This path of water from the mountains to the valleys in the underground may take years or hundreds of years. It is very slow. It is not a path like that of surface water, which takes hours or days. In this case, it's not a matter of hours. Unless you have cracks in the underground, you are in a karstic area, it may happen that it's very fast. But usually we are concerned because this water that comes out from the artesian wells, it's very convenient. It's very clean because it went through a long filtration. So it's high quality water, comes to the surface with limited effort because in many cases without pumping. In the case of the right well on the screen, I need pumping, but still limited. So convenient, cheap, clean, very good resource. And so today we are using a lot of it. It's less prone to pollution. We use a lot of it. But the question is this use sustainable? or not? How long does it take to recharge it? Is the recharge time comparable to the extraction, to the withdrawal time or not? We don't know. This is the problem. We don't know. And this is something that, it's difficult to understand today, where we have the illusion that we can control everything in nature. Actually, we have to realize that we are engineers and we are water resources managers, and we are dealing with climate. We have to realize that there are several processes that we still don't understand. So we don't know. Basically, what we do is to go by trial and error. So we take water from a well, and then if we see that the water levels in the well goes down, it means that the extraction is too much. So we try to decrease it. This is what we are doing in this region. We started extracting a lot of groundwater, and then we saw the levels going down. Keep in mind that once that the level goes down, you may underwent soil compaction, which means soil subsidence, which means that the aquifer cannot be recharged anymore because the voids have been occupied by the compaction. So you understand that in terms of sustainability, this is a big question mark for the future. And we try to solve it through inductive and deductive assessment. And we started with inductive assessment relatively recently, so you may find in Italy wells that go back to 1975 in terms of measurement, once every 6 months, 2 measurements per year. So you understand that you have like 50 numbers, or a little bit more, let's say 80 numbers. 80 numbers are really, really few. And then we try with models. And the question is, what is the spatial resolution, or the optimal spatial resolution? I said that I have to split the volume in elementary pieces, but how big should they be? Or how small should they be? If they are too small, it's a problem because it becomes more complicated and I need more information to define them. To define the permeability, to define the porosity, to define the soil properties in the underground, you understand? Not easy. If they are big, I need less information, but then the assumption of homogeneity is weaker. So this is interesting, it's very interesting, and it is one of the key issues that we face today in the face of climate change, in the presence of climate change. And the usual recommendation is try to diversify the sources. If a community takes water only from groundwater, it's a problem. We need to mix surface water resources, groundwater resources, to diversify the sources, because if one goes wrong, then there is the B plan, and possibly we recommend the C plan, the D plan. And what we recommend is to try to use the surface water resources because they are more sustainable. But of course, during summer, usually they are depleted because precisely for the very reason that surface water is faster, it means also that it rapidly depletes once that we get into the dry season. There is a question from the room. Yes?
Can we say that the getting out of water is caused by the buoyancy force with the help of tectonic movement?
Can you please repeat the question? And can we say that?
Can we say that getting out of water is caused by the buoyancy force with the help of tectonic movement?
Yes, but what we really needed to understand is tectonic movements has a different time scale with respect to recharge time. Tectonic movements is, recharge time I talked about 100 of years, but tectonic movements, it's a longer time scale. So I wouldn't take into account here the tectonic movements. What I would take into account here is how to model the movement of water in this aquifer on a time scale that is, much lower than that. Because what we really need to focus on is a time scale that is comparable with the time scale of water demands. So the question is, how can I model the groundwater resources that I could use, I should be able to use, and let's avoid tectonic movements. What you may take into account is land subsidence, which is a natural process which can be accelerated by groundwater withdrawal.
Do you think is the buoyancy force is responsible for the uplifting of water from the ground level to the surface level?
Yes, land subsidence, yes, if I well understood your question. It's responsible for, not for the uplift of water, but it's responsible for a reduced water storage after you withdrew the water from the underground. Is this clear? Okay. Yes, another question from the room?
Yeah, I like it, so I'm just trying to understand. The confined layer is there is unconfined layer like around it?
Yes.
On the top and on the bottom?
Not always. In this case of this figure that you see on the screen now, you have two figures. The upper one, you don't have an unconfined layer above. You just have a confined layer if you refer to the valleys, okay? If you refer to the lower section. We may say that this layer is confined in the lower section, unconfined on the sides. But actually, let's focus on the valleys, because usually we need to take water from valleys. And groundwater resources are not used in the mountains usually because they are too deep, okay? So in this case, if you focus on the valleys, you don't have an unconfined layer above. If you look at the bottom figure, it's a different configuration. You have an unconfined layer. Actually, in alluvial areas, which most of the valleys are, you get several layers, one over the other, because they are the result of the deposition of several layers of sediments. Alluvial areas are formed for the deposition of sediments in different periods. And depending on the size of the sediments, you have greater or lower variability. And therefore, you get several aquifers. But this is not only the case. You may have also cases in which you have only the unconfined one, and nothing more, or you may have cases like the upper figure where you have only confined aquifers. Is this clear? Because the question was for those who are attending remotely if there are always confined, unconfined aquifers, and then in the depth there are always confined aquifers. Actually, the situation may be extremely diverse. I hope I answered your question. Not really, so try to state it again then.
No, it's okay, because I came late, so I will check it later on.
Okay, very good. Okay, let's forget these two figures and let's go back to our relevant page, deductive methods to groundwater. Okay, now let me go to the PowerPoint presentation. This is my elementary volume, which I am referring to, okay? It's a cube with the size, the x, the y, the z. We call it our control volume. It's fixed, not moving. Keep in mind that groundwater is moving slowly. So very often we don't need a Lagrangian description. It's fixed in space, the volume. And I anticipate another thing. You may know that energy losses in fluid mechanics, energy losses in pipes are proportional to the square of velocity. So the more the velocity, the more the losses given by friction, also in surface water bodies, in rivers, but in a nonlinear way. So the more the velocity, the more the losses, but the dependence is on the square of the velocity. In groundwater flow, we can easily make a linear approximation with energy losses proportional to velocity. Okay, so not to the square of velocity. This is a big difference. It's a big simplification. We are lucky for that. Simplification assumption that we can take because the flow in the underground is much lower. And you may ask me to give a number. So keep in mind that when you have a flood, water can move in a torrent under a flood, can move with a velocity of 1, 2, 3 meters per second. 3 meters per second is very quick. But also 1 meter per second is really a huge velocity. When you get very calm flow in rivers, you may go down to 0.01 meters per second, 1 centimeter per second. This is very slow, okay? 1 centimeter per second is very slow. In groundwater, you may go down 3 orders of magnitude, so 0.0001. So 1 millimeter per second, 1/10 of millimeter per second. In fact, usually we describe permeability not in meters per second, but in millimeter per hour. Okay? Permeability is described as a physical behavior of the soil, which has the unit of a velocity. And it's called, let me be more precise, it's called hydraulic conductivity. It's related to permeability, and it's the velocity of the water flow in the underground, basically. And it's very small. Okay, so this is our control volume. We need to apply mass balance. Good. So it is in principle easy to apply mass balance. We have to assume that the fluid is incompressible. So mass density of the fluid is constant. And let's assume that there are no sources of mass in the control volume. So in this cube here, you don't have springs inside. You have flow through the sides and storage that changes because you have these flows through the sides. So if you have inflow higher than outflow, you have an increase of storage. The opposite is true. If you have outflow that is higher than inflow, you have a decrease of storage. Now let's express then the mass balance with this very simple equation. It is similar to what we wrote for the linear reservoir. Basically, the change with respect to time of the storage W, which depends on 3 coordinates plus time. So W depends on X, Y, Z, and T. 4 coordinates. 4D problem. The change of W with respect to time is equal to Q in minus Q out. What is Q? It's flow. It's flow. So it's volume divided by time. In fact, you see the left-hand side is a volume divided by time. The right-hand side is a flow, difference of flows. So volume divided by time. Flow is defined as volume divided by time. Okay. The problem is that also the flow changes in the 3 directions. So the flow is not a unique direction in the groundwater. It's not like a river. In a river, you have flow that is mainly in a unique direction. It's downstream, okay? In the underground, you have flow that is changing in the 3 directions and time. And this flow goes through the 3 directions of space, and therefore is through the 6 faces of the cube. Okay, let me go back to this figure here. Any side, any face of this cube is subjected to flow through. So we have three flow components, Qx, Qy, Qz.
And also we have three different infiltration rates also in circle.
Infiltration rate is through the sides, through the faces. This is possible, yes? It's possible. Because this elementary volume is not necessarily saturated, okay? It is an elementary volume of soil through which we have flows. So if you assume that the gray side, the gray face is the face above, you may have infiltration from above, yes? Which is a flow in the Z direction. Okay, but of course you have flows through the gray face, but there is another face in the bottom that you don't see here. It's another flow in the Z direction. So you have 6 sides, 6 faces in a cube, and every face may be subjected to passing flow. So what is the conclusion? In this equation here, Q in and Q out have to be expressed through 6 components for Q in and 6 components for Q out. Actually, they are 6 components, and depending on the sign, you have Q in or Q out. But I need to, in a way, to provide a more complicated representation for Q in and Q out. You understand why I need a complicated notation? Because now I need to split this Q in and Q out in 6 components. Okay. So the next slide will be a little bit heavy. Okay. But let's read lines one by one. To estimate Q in, now we can, let's look at the first line. Volume per unit time into phase X. Qx, which is the flow along the X direction. It depends on the 4 coordinates, again. Because even if it's along the X direction, if you change the coordinates, you have the flow along the X direction changing, times the area of the face that is orthogonal to the X direction, which is given by, look at the far right side, the Y, the Z. The area AX of the face along the X direction is given by the Y, the Z. Let me go back a couple of slides. You see that if you look, for instance, at, I said the area along the X direction, look at the X direction, look at the lowercase qx, what is the area of the yellow face, which is orthogonal to the X direction? The yellow face is what I called AX. It's the product of the Y, the Z. And let me now go back to the slide. You see, QX times AX, it is equal to QX times the Y, the Z. Okay, good. Volume per unit time into phase Y, it's the same expression. The only thing I have to change X with Y, and I have to change when I go to compute A, Y, I have to change Y with X. So what I obtain is QY, it's equal to QY, the volume per unit time into phase Y is QY, the X, the Z. And the same for the third coordinate. Okay, so I got the 3 components of flow. Okay, now, what are here the lowercase q? The lowercase q are volume of fluid per unit time and the unit area. of the phases. So you see that I used the lowercase q here as opposite to the uppercase q in the previous slide, because these are flows per unit area and unit time. Okay, so let me go back to the previous slide. I used here the capital Q, which are flows, so volume per unit time. And in order to express these flows, I pass through the three components, but I express them in terms of lowercase q per unit area. And then, of course, I multiply them by the areas, and I get, again, volume per unit time. Okay. So now I can compute the total inflow volume, Q in. Q in, look at the line that is close to the bottom, Q in X, Y, Z, T. There is a X missing here, sorry, I didn't notice that before. But Q in, uppercase Q in, is given by what? Is given by the flow through X plus multiplied by the area X plus the flow through Y plus the flow through the Z direction. But the flow is passing through two phases. So the flow along each direction is entering from one phase and then is exiting from the opposite phase in the same direction. And therefore, I have to account for these two components. So I have lowercase qx plus the change of lowercase qx along the x direction times the x. So this is the flow through one phase, lowercase qx, and the second addendum is the flow through the opposite phase in the same direction. And this is Q or here it's actually it is indicated as Q out, but it is the same. Okay. Okay. This is the total flow. So we can substitute this expression in the bottom here in the previous expression here. Yeah?
In previous pages in here, could you please tell us the unit of the Qx or Qy unit?
The unit are for the capital Q, for the capital Q, the unit are volume divided by time. For the lowercase q, the units are volume divided by area divided by time. So it's a length divided by time. But then you multiply by the y, the z.
Isn't the Darcy velocity?
No. Let's forget about the Darcy velocity. This is mass balance.
Because by multiple the units, it must be volume unit is the cubic of meter. Yeah.
Yes.
Okay. We have the area square meter.
Yes.
Plus multiple by.
If the result.
I think it's much more divided by area to get the units of the cubic meters.
Yes, because the lowercase q is divided by area. This is what I said. It's volume of water per unit area and unit time. Lowercase q. It's a specific flow, okay? It is what is called a specific flow. Of course, you have to, the dimensional homogeneity is to be verified. And this is why I use different symbols. upper Q and lower Q. Okay, now if we substitute here, we have the change in volume, which is equal to inflow minus outflow. And inflow is just given by the lowercase q multiplied by the areas. The outflow, as I saw in the previous slide, is given by inflow plus the change. So the notation is heavy, but the concept is just what was depicted here. This is the concept. Is change in storage is equal to inflow minus outflow. And then I go forward. Change in storage is equal to inflow. Inflow is just given by specific flow times the area. And the outflow is specific flow plus the change in specific flow times the area. It's a mass balance. It's a very, with a heavy notation, it's a very simple addition. This is an addition, inflow minus outflow. And the outflow is given by inflow plus the change. It's a sequence of additions. And you can already see here that some terms will annihilate each other. Because the inflow, when I subtract the outflow, some of the terms go out. They go. So it is going to become simplified. It's just, again, an addition. Mass balance, remember, it's an addition. Nothing more than that. Okay, in fact, you see that some of the terms go out. Look at the last line. This is the result. Because the lowercase q minus lowercase q, they go out. Only the changes remain. So the change in volume is given by the change of flow along the x direction. The change of specific flow times the area on the x direction and the x that remains from the previous computation, because it's the change along x. Okay, so change in storage is related to flow along x, change of flow along x times the x, and area, minus the other components along y. So the result at the end of the story is just this last line on the screen. Change in storage is equal to change in flow along each direction multiplied by the elementary dimensions of the volume. And the only thing is that what is the complication here beside the notation? The complication is the 4 dimensions. Not because it's complicated mathematically, but because I need to define the flow, the flow components in 3 directions of space and time. It is, the information that I need is massive. It's not the computation, the problem. Computation, I have PC today that allow me to do that. The problem is the information. Okay, also, what is the problem here? The problem is that I have one equation, which is expressed in 3 directions. So, but let's see, one equation and several unknowns. I cannot resolve this equation alone. I need another equation. Okay? Okay, at least another equation. So you can already understand that here at least we have 2 unknowns, which are storage and flow, with only one equation. Okay, now let me define property of groundwater media, which is fundamental, and it's the volumetric specific storage. This is a physical property. And it's called very frequently just specific storage. How it is defined? It's the volume of water that an aquifer, a groundwater body, releases from storage per volume of aquifer. So it's a specific volume of water that an aquifer releases from storage per unit decline in hydraulic head in the aquifer, which is hydraulic head is pressure. But in hydraulic head is expressed as pressure because hydraulic head basically is the depth of water which is putting the aquifer under pressure. So it has the dimension of a length, and a water column, a given water column gives pressure because of the weight of water. And therefore the hydraulic head is a synonym of pressure. It has the dimension of a length, and therefore the volumetric specific storage has the dimension of 1 over length, because it's a volume of water released by unit volume of aquifer. So this ratio is adimensional, divided by the hydraulic head, which is a length. So the volumetric specific storage has a dimension of 1 over length. And what is the meaning of this volumetric specific storage? The meaning is that if you have a sponge that is under pressure of water, and you suddenly decrease the pressure, the sponge releases water. Because the sponge is elastic, it's a little bit, it expands if you decrease the pressure, and by expanding pushes the water out. And this is the volumetric specific storage. It is the property of the aquifer that when you reduce the pressure, you release the pressure, then it releases water. And how can we reduce the pressure? For instance, by taking water from a well. The well is a water column over the aquifer. We take water from the well, and the aquifer is getting less pressure and releases water. This is the volumetric specific storage. So in a way, even if we assume that the fluid is incompressible, we have to take into account very important properties of aquifers, which is the fact that if they are put under pressure, they store more water, not because it's the water that is compressed, but because the pressure brings water also in all the pores, in every single pore, and also water expands the aquifer a little bit. Okay, because by pushing each particle of the soil away, then water can occupy some more space. But when we reduce the pressure, then, okay, very good. So what we can say through the volumetric specific storage, we can express these flows along these specific flows in terms of volumetric specific storage and hydraulic depth. What is the purpose? The purpose is now to introduce in this equation the variable hydraulic depth, because it's what I can measure in wells. So in the wells, I cannot measure the flow. I can measure the depth of water. And therefore, I want to bring inside this equation the hydraulic depth. And therefore, the idea is to find a relationship between depth and flow. And this is the volumetric specific storage. This is the idea. Let's find a connection between depth and flow. And therefore, the equation becomes like this. So you see that I don't have anymore the change in flow, I have the change in depth. And therefore, I can write that the change in volume with respect to time is equal to the product of change of volumetric specific storage times change in depth, which is equivalent to what was written before. Okay?
What is
It's volumetric specific storage. SS, volumetric specific storage. It has a dimension of 1 over length. Okay? And then if you look at here, then you have this expression. If you look at the third line, if you look at basically at the change of, let's start from the beginning. If you look at the change of storage is given by the volumetric specific storage that multiplies the change in hydraulic depth minus the various flows. This is, let's take a bit of time to read this, and then I will continue to comment, okay? And let me just go back to the previous slides so you remember. There is, let's look at the bottom line. So the change in volume is given by the 3 flows along the 3 directions. Okay, so minus Qx, minus change in Qx, minus change in Qy, minus change in Qz. And then I introduce here the change given by the volumetric specific storage. And then, so you have the change in volume is given by the change given by the variation of hydraulic head minus the flows along the 3 directions. And I think that, and then I go on the web page after this one. Let me go on the web page because this one is more, there is more descriptions. Let me refer to here because the slide was, there was a repetition. The slide was not really correct. There was a repetition that was misleading. So please let me focus on this, okay? Let's forget about the slide. I will correct it and we'll put it a revised version available for download. But you have to refer, as I said, for studying on the web pages, correct? So let me refer on this. So this is what I wanted to focus on after the introduction of the volumetric specific storage, okay? That's it. Let's focus on this, okay? So this is clear. Okay, so this is another way of expressing the change in volume. Now we can combine the 2 equations. Yes, please.
So this replaces capital Q out, Q and
Yes.
Q out.
Yes, let me focus the first, the previous one. Let me put on the screen the previous one. 1 second. The previous one, it is this. And this is what we reported in the slide, which is correct. This is the previous one, okay? If you look at the last line. And then by introducing the volumetric specific storage, I replace this the right-hand side, and which becomes this one, correct? I hope you understand now. Sorry for the slide that was misleading, okay? Now, I can combine the two versions. I can eliminate the change in storage, by combining the two versions. So let me just go back again to the previous. This is one expression for change in storage. Look at the last line. This is another expression for change in storage. If I combine them, I eliminate the change in storage. Why I want to eliminate it? Because I cannot measure the storage in an aquifer. It's a variable that I cannot measure. So I prefer to have a relationship not between storage and flows. I want a relationship between hydraulic head and flows. So by combining these two, now I get the relationship between hydraulic heads and flows. Let me just show you what is. It is this one. Just 1 second, I am with the mouse. It is this one. You see a relationship between, now the storage disappeared. I have a relationship between the flow and the hydraulic head. Still, I have two unknowns, hydraulic head and flows. What I obtained is I substituted, as I said, the storage with hydraulic head. Storage disappeared. But for doing that, I needed to introduce SS, which is the volumetric specific storage. Good. Now, at this point, as I said, we need another equation. And then it becomes the time of the Darcy equation that you mentioned before. The Darcy equation is a conservation of energy, conservation of momentum, but when you put it in scalar form, it's conservation of energy. So at this point, we have to introduce a relationship between what? Between head and flow. Another relationship, not a mass balance. Mass balance is on the screen. I need another relationship between flow and hydraulic head. And what can it be? What can it be? Conservation of energy, which is the Darcy equation. Just 1 second that I try to understand why it looks like there is no connection for a moment. Let's try to wait a little bit. Okay, the connection should be back. I don't think you lost a lot because I didn't say anything. When I saw the connection going out, I stopped. So just let me know if there is something that you feel it's missing. Okay, so as I said, I need an additional equation here because I have two unknowns and I need to introduce the conservation of energy. Let's go back to the web page, but before doing introducing the second equation, let's take the previous relationship in a simpler form. So what I can do is to eliminate from this equation here the three products, dy, dx, dz. You see that I can divide each member of the equation, the left-hand side and right-hand side, I can divide it by the elementary volume, the x, the y, the z. Perfect. If I do that, I obtain another form of the equation, which is much simpler. It is this one. It is much simpler. Okay? In terms of notation, it's much simpler. And I can use the divergence operator to write it in compact form, which is this one. I can use the operator nabla to identify the derivation of Q with respect to the three directions. Okay, this is in compact form, but still it is in compact form, but still I have two unknowns, Q and H. So this is now the time of introducing the Darcy's law. Keep in mind this equation, there is a note here, is known in other fields as the diffusion equation or heat equation, because the flow of water in the aquifers indeed can be described by the diffusion equation or the heat equation. Okay, now you see here the above equation has both the flux Q and the head H unknown. Therefore, it's necessary to couple the continuity equation, the mass balance equation is also called continuity equation, with the second equation, which is the momentum equation. And let's call it Darcy law for the case of aquifers. Okay? Darcy's law is, an excellent example of a brilliant intuition that was derived after an empirical experiment. What Darcy wanted to do was precisely to describe the flow of water in a porous media. And he made a very simple experiment. And there is a Wikipedia link here. I think it is interesting if you look at it, because you can understand what was the intuition of this person, and you can understand really much better what we are talking about. So he made an experiment. He forced water to flow through a porous medium. And let me see if there is a sketch that is more, because the sketch here is not really very useful. So let me just, this is not very understandable. Let me just show you another, and let me do like this. I need to close these pages. They are not useful anymore, okay. And then let me just open another one and look for Darcy Experiment. And then we look for the images. Okay, this one is very good. This one is very good. Let me just open the image here. Okay, so this was what Darcy did, which is very, very simple. And he basically took a sandbag, put it vertical, and poured water from the top, and then water was flowing from the bottom. And what he did was to measure the water pressure at the entrance of the sandbag through a piezometer. You see, this is basically a tube measuring water level. So he was pouring water with a pipe in the input, and then he measured the water height, which is a synonym of the water pressure at the entrance. And then he also measured the water height at the bottom of the sandbag. And of course, you see that there is a decrease of water depth, which means a decrease of pressure, which is normal, because by pushing water through the sandbag, you lose energy. And losing energy means, what is energy in a fluid, in a moving fluid, is given by a position component and a kinetic component. The kinetic component, you can forget about it, because it's very slow. The movement of the flow is very slow. And therefore, the energy is just given by the position component, and the position component in this case is pressure. And then he measured the decrease of pressure, which means the decrease of energy, that was taken by the water flowing through the porous medium. It is a very simple experiment, but with this very simple experiment, he introduced one of the more fundamental laws that we use in water resources management. It's amazing, the intuition. And basically, he could see that the loss of energy is proportional to to what? Is proportional to the flow. The loss of energy is proportional to the flow. He discovered that there was a direct proportion between loss of energy and flow. And this is what we have to introduce in our system. If we want to relate the flow with hydraulic depth, this is precisely what he did here. You see that he measures the change in hydraulic depth depending on the flow. So it is what we are looking for. So basically, in my website, you see a complicated description. I need the momentum equation, but actually, if I want to simplify this, momentum equation is conservation of energy, but if I want to simplify this, it's just sufficient that I see that I say that I need to introduce the Darcy's law. Now, what is the expression of the Darcy's law? It's, you see here, a direct proportion between flow and change in head. But if I introduce these three relationships, why they are three? Because I am considering three directions. If I introduce these three relationships inside my previous equation, I am okay. System is solvable. And now there is a bit complicated mathematical development, but it is just a simple substitution, okay? So you see that on the blackboard you read on the screen, by substituting in the above equation, one simply obtains, so let's see what is the source equation. Basically, you see here that I have these three relationship, proportionality between hydraulic head and flow. Then I can substitute here. I can simply substitute in this equation here. And if I substitute the left-hand side with the Darcy law, I obtain a resulting equation where the unknown is just one, it's hydraulic head, which is what I want to describe. So let me now make the substitution. And you see that here is the result. Sorry. I want to open it in a new. It's only one equation where I have only one unknown. It's the hydraulic head. In three directions, plus time, depending on the volumetric specific storage SS, which is a fundamental property that I needed to introduce to remove storage from there. Hydraulic head is something that I can measure on the field. So you see that in principle, if I had for any elementary volume a well, I could measure in each point of space and each time, I could measure H, hydraulic head. And then I could describe this equation, and I could also estimate SS from these measurements. SS is a parameter. It's something that I cannot really measure on the field, but by using these measurements and this equation, I can get an estimate of SS. Yeah, so there is a question in the room, please.
Why it doesn't consider the hydraulic conductivity in each dimension? I mean that Kx, Ky, and Kz.
Yes, because there is an assumption here, which I forgot to mention, but it is on the web page, that the hydraulic conductivity, which is, this is something that I didn't say, the constant K of Darcy's law is called hydraulic conductivity. And there is an assumption of anisotropy, which means that hydraulic conductivity is constant along the three directions of space.
Or maybe the structure of the soil is different in each dimension. I mean, that because it's related to the hydraulic conductivity.
Yeah, but I mean, this is an assumption because in principle, K should, as you rightly said, should change along the three directions. In principle, this is possible. I mean, if you think at the two horizontal direction, it is an assumption that is reasonable because we are working at the very local level. And therefore, it is reasonable that the direction y and x, the permeability doesn't change, but along the vertical direction, usually you have a change in permeability. And because of soil compaction, which operates in different ways along the three directions. But in any case, my reply to your question is, you are right. This K should change in the three directions. And in this case, there is an assumption of anisotropy that has been introduced in my web pages to simplify the notation. In principle, K may also change in time because there might be other influences that change the permeability in time. Like, okay, that's also the properties of the fluid can change in time, but we made some assumptions. And let me stress once again that K, which is the proportionality constant of the Darcy's law, it's called hydraulic conductivity. By the way, Darcy's experiment worked in only one direction. He only studied the propagation in 1D, which is the vertical direction. But indeed, again, you are right. K in some models is allowed to change in the three directions. This K is actually another parameter that compares in this equation, which I forgot to mention. It's not only SS, but it's also K that is to be estimated. It is not easy. It is not easy. Other questions? Because basically we have finished this. This is what you see on the screen. It's the groundwater flow equation. And this is the equation that we have to integrate if we want to model the groundwater flow. Do you have any other question on that?
Modeling of in this equation in the answers. The modeling of the porous media in answers, it's very interesting that it's used this kind of equation, and it's want to put the especially hydraulic conductivity in each dimension and all of the parameters, and we can modeling this in the answers very easy.
Okay. In what say again? In
answers.
In answers. Okay. Okay. But because I guess that you had some other courses teaching the groundwater flow equation.
In the bachelor's.
In the bachelor. Okay. I see. In answers, yeah, it is. It is. But you have several packages that you can use, and there is a package. First of all, before I make this comment, let me just go back to the web page, because you can write this equation in a more compact form by using an operator, because let me just show you. Because the textbook, actually, they present it this way. By using the operator lambda square, nabla square, sorry. So K, let's assume that K is constant, so you can bring K out of the derivative, and then you get a nabla square of H, which is equal to SS blah, blah, blah. And the blah, blah, blah is the right-hand side, okay? Sorry for... And in steady state condition, you get the equation that you see here, which is a Laplace equation, okay? And in steady state condition, if you annihilate the dependence on time, you get a Laplace equation, which is an equation that is widely used to describe potential flow. And I think you probably already met the Laplace equation. If you are interested, there is a Wikipedia link here. Now, let me make a comment. You said that you may use ANSYS. actually for modeling groundwater flow, there is a package that is widely used, which is public domain, which is ModFlow. ModFlow, it's a USGS package.
The mostly is especially for the groundwater.
Yeah.
Very interesting.
Yeah. This is ModFlow. It is freely downloadable. It's tough. It's not user-friendly at all. And the reason is not really, it has very nice interfaces, so it is user-friendly. The problem is that when it gets stuck, because it's numerical integration, so very often it gets stuck, you need to be quite expert in solving the problem. It is a bit tough, but you see that also the output is nice, and this is not commercial. There are some interfaces that are commercial, but this is not in principle, and there are several interfaces that are free. And it is widely used by water boards all over the world. And the purpose is precisely to try to estimate the sustainability of groundwater exploitation. So a bit tough. I think now we can make a break, and then the next hour I will focus on the exercise. I will start because it's a bit long, the exercise on IMOD. I see that there is a message in the chat. Let me just check. I reply later, okay, after the break.
Right.
I don't know if you should do. I don't know.
Okay, so two things. Before we move forward, two questions have been addressed to me and I want to reply. So there was a first question related to some more clarification on what is a confined aquifer with respect to an unconfined, and I give you some indications on where to find this, because everything is on my web pages. So if you go to Sustainable Management of Water Resources, one of the previous lectures, there is in the bottom a description of how aquifers work, which is taken back in the current lecture. So I think it is clarified by these two figures how confined and unconfined aquifer work, and please stick on a very schematic representation. So let's forget about complicated situations where a confined aquifer may be in communication with an unconfined one. Because if you think, for instance, at wells have different windows, we call them in this way, which means that they take water from both of them. So there are several, we distinguish between phreatic wells and artesian wells, but actually there are some wells that are mixed. So there are some aquifers that are mixed between confined and unconfined. Let's forget about these very diverse situations, and let's focus in our treatment on a simplified schematization. So the layer dividing an unconfined aquifer from a confined one is not permeable. So let's take this as a layer that is absolutely not permeable. And then, of course, one may say, but if I have some permeability in this layer, okay, but these are more complicated situations. We want to stick on a very simple picture, because even with a simple picture, you see that the development is complicated. And then let's simplify it, okay? So you can find everything here. Second question that I got, it's should we learn this formula by memory for the exam? So, first, in principle, I don't require that you learn anything by memory. What I may require, if you want to pass the exam with a full grade and may be allowed, is that indeed when we make a proof during the lectures, which means that we start from some assumptions and we do some mathematical development, what I really would like is that you learn the proof, and if you learn it, it means that if you're asked at the exam, you should be able to repeat it. So I think that the groundwater flow equation, and this is IMOD. IMOD, we did some mathematical development, and it may happen that I ask it at the exam. The same for the groundwater flow equation, and there are all the steps here, and therefore, if you just remember the assumptions and the concepts, you should be able to develop it. But when I make an exam, usually I try to adapt my questions to the ability of the student. And therefore, if I see that the student, for some reason, has given a lower priority to the exam, which means that the student is not aiming to get the max mark, I don't ask questions like IMOD or the groundwater flow equation, which means that, of course, also the mark is related to this. Maybe that you don't take the laude, you don't take 30, but you can still get a good mark like 27, 28, or 26. It depends, even if you cannot repeat the full development of complicated proofs. So I think this is also the way to adapt to your diverse background. And I tell you, in some cases, when the student proved that there was a very good knowledge of the concepts, the assumptions, and the motivations that bring to obtain a mathematical development, even if the student is not able to repeat it step by step. I gave sometimes a mark of 30, maybe not allowed, but 30, yes. Because what is important is that you remember the concept, the assumptions, and, for instance, the idea of introducing the volumetric specific storage for, in a way, eliminating the storage from as a variable from the groundwater flow equation to substitute it with the hydraulic head for the reason that it can be more easily measured. So if you are able to explain that what is the groundwater flow equation, where do we start from? Conservation of mass, conservation of momentum, which implies conservation of energy. You can state the assumptions, and you can state the main, the milestones of the development. It's not a big problem if you don't repeat it step by step, okay? The important thing is that you prove that you have got the concepts. And in case you instead aim to get the max from this exam in terms of knowledge, which means also that you get the max in terms of mark and in terms of laude, if it is the case, then of course I suggest that you can also show that you can provide good performances in the mathematical developments. I think, I hope this is clear. Finally, let me just say that I have a couple of final considerations to make on the groundwater flow equation, which I would postpone to Thursday, because I think you had enough for today, okay? And so on Thursday, I will make a couple of final considerations that you can find here. There is a box, and also there are some issues related to application. The box is useful because if you want to get more information on the volumetric specific storage, okay? But I will make comments on Thursday on that. Yeah, questions?
Are these parts, for example, this equation part and the Helmut model, the exam in oral part? Or?
There might be in the quiz some specific questions, and a question on the quiz could be, what is the volumetric specific storage? And then there are three definitions, and only one is correct. This could be, but not on the mathematical development in the quiz, okay? Or another question in the quiz could be, what is the correct expression for the Darcy's law? And then you have three or five possible formulations. Or another question could be, what are the assumptions conditioning? What of among the following five assumptions, what are the assumptions that refer to the Darcy's law? And then there might be incompressible fluid, yes, perfect. And then there might be something I need to look at but you will find the perfect correspondence with the web pages, okay? So I give you some assumptions, and then you have to select what is the correct one, okay?
So we have oral and quiz, both chapter.
Yes, you have a quiz, and then after the quiz you have an oral, okay? And the oral is very short, but the question for the oral could be, if I see that your quiz is very good, I may ask groundwater flow equation. And then depending on your reply, because my question is never something that is very specific. I don't ask, please provide a full proof of the groundwater flow equation. My question is groundwater flow equation. And then you decide how to reply. If you can remake the proof, then of course you should do it. Otherwise, you can just say something like it starts from conservation of mass and conservation of energy under these assumptions, and then we get to a relationship between hydraulic head and whatever with depending on hydraulic conductivity, and then you can skip it. And of course, if you skip the mathematical demonstration, the evaluation takes into account your performance in that. Okay. I aim to give you, by the way, an example of quiz before the exam. So maybe in May, I need to wait a bit. Okay? So let's go to the exercise because, as I said, I think today we had enough. So let's go back to the web pages, and there is IMOD here somewhere, and calibration of the Imodraeforanov model. And we still don't know what calibration is. We will talk about calibration on Thursday, but let's rephrase the exercise in application of the Imodraeforanov model, which is more or less the same. And there is an R code that is proposed for resolving it. But let's look at the text before than that. So in a river cross section draining a catchment whose area is 1214 square kilometers, river flow data have been observed at hourly time step for a period of 1 year. At the same time, precipitation and potential evapotranspiration have been estimated. The related observations can be downloaded there, but the links are available on my website, so you don't need to cut and paste them. By using the above data set, the IMOD model should be calibrated, meaning that the parameters of the IMOD models should be optimized by using an objective function. Let me rephrase this requirement in this way. By using the above data set, we have to apply the IMOD model to simulate the observed river flow. Okay, so you see that we have river flow data, precipitation, and potential evapotranspiration. We have to take precipitation and potential evapotranspiration, plug them into the IMOD model, and get a simulation of river flow to be compared with the observed river flow. This is what we have to do. Okay. Apply the IMOD model by using precipitation and evapotranspiration data to reproduce the observed river flow. And then we will compare them. We will have a simulation and observations, and we will make a comparison to see how good the IMOD model is. Of course, you see that, you know that the IMOD model is counting 5 parameters. We have to plug in trial values for the parameters to get this simulation, trial values, okay? Good, and let's forget about the other requirements for now, because let's focus on the first part of this application, which is what I said, application of IMOD. Very good. Now let's go again at the website. There is a suggested R code. First, let's look at the data. You see the link to mean areal rainfall and evapotranspiration data. This is the input for the IMOD model. I clicked on it. You see that it is a text file. The first column is hourly rainfall in millimeters per hour. The second is hourly evapotranspirations, same unit, millimeters per hour. They are synthetic data, not observed data, but let's forget about this. This is not important for now, but they are hourly data. This is important for 1 year. So I want to stress once again, when you get a data set, the first thing that you have to clarify is the units, which implies the time step. So you have to understand what are the data about. So we have here rainfall in the first column, evapotranspiration in the second column. We have the units, millimeters per hour, and we know that they cover 1 year at hourly time step. This is all what we need. Okay? And of course, the first step that we have to perform is to upload these data into R. Okay? Very good. Now, can you please remind me, when we introduced R, we used R Studio, correct? Good, perfect. Okay, so we have to upload this data into R. But before uploading, let's look at the second data set. River flow data. River discharge in cubic meters per second, and they are hourly data, where it is specified that they are hourly in the website. If you go back here, you see hourly data for 1 year. So the time step of rainfall and river flow data is the same, hourly. The units are different. Millimeter per hour rainfall, cubic meters per second discharge. Be aware of that. Perfect. Now let's start our session. And in order to do that, I have to share my screen for a second. So just who is attending remotely, don't be concerned, you will get the screen back soon. But I need to, because as you know, I need to remotely connect to another PC because our studio is not available in this PC. Yeah, I remember I have this problem because it is not connecting from here. So let me try again, but I think it is a problem with this PC. Yeah, no way. Okay, so one second, and let me try to get give me 2 minutes because I have to install R rapidly, and then I will check if I can run our studio here. Otherwise, I will run only the R console, which is anyway for this half an hour would be enough. While I am installing, please open an R studio, okay?
So do we have this for the exam?
Sorry?
Do we have the art studio for the exam?
I don't understand the question, sorry.
Do we have this for the...
I clarified in my web pages that the exercises are not asked at the exam, okay? If you look at my web pages from the beginning, if you missed something, please go back and read because it is very easy to read. It is very short, okay? I am still installing, just 1 second. Thank you. Okay, now let me check. So I'm not allowed to install RStudio, so let me start an R console, and you can work in RStudio in the script window. It's the same procedure, so you can follow me. Okay, I have this R console which I am now sharing. I am changing the font so you can see better. Really, this mouse, it's a nightmare. Okay, now you can just copy what I am writing on the console on your RStudio script window, okay? Now let's go back to the website. There is a proposed R code. Which I am opening. I open it in the notepad. Okay, very good. Now, first, we need to upload the data. And to upload the data in RStudio, I suggest that you save the data file on the desktop. And in RStudio, under Session, select the working directory as the desktop and upload the data file by using the instructions that I am using here. Don't use the RStudio facility menu to upload the data because it is uploading the data in the form of a database, which is not really the easiest way to get it. So again, what you have to do is to save the data file that you find linked in my website in the desktop, and set the RStudio session working directory, again, desktop. And then you go into the script window and you use these two instructions. You copy and paste them from the website, my website, to the script window, and you run them. Okay? So I do it, copy, I go to the R console. You should go instead on the script window, and I copy them here. The only thing is that I'm not sure I downloaded the files before. Let me download them. I save the file as in the desktop, save, and I save also the river flow data. Save as in the desktop. Very good. And then I can go in the R console, and let me just copy it one by one. The first here. Control C. I use the keyboard because the mouse is really normally, okay. And then I have to change my path because I have to go in the desktop, but you don't need to make this because if you're using RStudio, you just need to set the working directory on the desktop. In my case, I have to do it, so let's see. As I said, you don't have to repeat this. One second. Okay, here I am. Truncated, okay, I see. Sorry, because I have problems with this specific PC, so don't be concerned by what I'm doing now, because I can't really use the mouse, so it's a nightmare. Let me see if I can try to... okay, now it looks much better. Let me see, desktop, okay. Properties. Very good, let's see, users, okay. Users. Alberto, all users, no. Okay, Alberto Montanari, very good. Desktop, very good. Desktop, very good. Rainfall, let's see. I don't understand why. Ah, it's in download, okay, very good. Download, oh, kappa. Download. Rainfall. Okay, I got it. This is my instructions, but I forgot skip equal 1. Good. This is what you should get from executing this instruction in RStudio after setting the working directory. You should get a confirmation that it reads 7,520 items. Okay. Okay, so I read it. Now I need to read the river flow data. So let me see what is the name, is discharge. And I don't remember if I had to skip it. Let me see. No. Yeah, skip. Yeah, it's here. What I just digitally this one. Okay, now one thing. Okay, and I just want to call it QOS. Okay, now I uploaded rainfall and river flow data. let me just make a check, a plot of the river flow data, plot QoS. This is not in my proposed R script. It's just a check that I make, type equal line. And why I am making this check? Because I want to make sure after I uploaded the data that everything is fine. This looks like river flow data. There are no outliers. I think it is fine, okay? This is just a check. I can close the graphic window either by clicking on the cross here, or I can just type here dev.off, and then it closes the graphic window. This is just instruction that I give to you in order to increase your, okay, your knowledge and your background. Okay, now the problem is that the river flow data that, the rainfall data that I uploaded, rain evapo, this is a vector, while, if you remember, originally the file was a matrix with the first column rainfall, the second column evapotranspiration. So now it is instead a vector. For instance, if I take the first 10 values of this vector rain evapo, you see that there is one rainfall, one evapotranspiration, one rainfall, one evapotranspiration, because the file was read line by line. Instead, I have to read the file column by column. So what is the way of converting this, converting the vector into a matrix in columns? You find the instruction in the proposed code, which is an array function. It is this one. So what I'm saying to the program is to transform the vector rain evapo into an array which has dimension, 2 columns, 8,760 rows. Okay, so I copy it and I put it here. Now, if I again want to see rain evapo, now I have to give in between square parentheses the size of a matrix, not a vector anymore. And you see that if I give to the program the instruction to plot the first column and the first 10 lines, I get 10 rainfall data. If I want instead to get the second column, 10 lines, it's evapotranspiration data. Perfect. Now I have the data into a matrix. In order to use them, let me, and I look at the code again, let me put these columns into 2 vectors. Why I'm doing this? Just for the sake of clarity. I don't need to copy these columns of the matrix into 2 vectors. I'm doing it just for the sake of clarity. So I get a vector with precipitation and a vector with potential evapotranspiration. So Control C, copy, paste. Okay, now if I make P110, I get the same as rain evapo. Sorry, I don't understand. I forgot the. I got the same as rain evapo, column 1 from 1 to 10. Okay. Perfect. Now I have P. I can plot it. Plot P equal line, just in order to check it, that everything is fine. Okay. Fine. This looks like a hyetograph. The hyetograph is the graph of rainfall. No outliers, everything is okay. And if I plot EP, what do I get? Plot EP. You see that the resulting plot is something that looks strange, but actually it is not, because potential evapotranspiration, this is 1 year of data, is computed at monthly time scale, and then split into hourly time scale just by keeping it constant for each month. So you see here 12 steps. evapotranspiration potential is low in January and December. It's highest in August. It is fine. Okay. Now, what should we do to move forward? Move forward, I am ready to write a function that applies IMOD. It is convenient to write a function because when we predict that a code should be applied several times, and IMOD, I mean, it is useful that I apply it several times because I may want to try several parameter values. So when I predict that a code should be applied several times, it's much better to write a function because by writing a function, it is very easy to repeat it. Okay, and the argument of the function may be, for instance, the parameters of the model. And now this is what we are going to do. I don't think it is worth starting now. We will move forward on Thursday. I just want to make a comment before moving forward. You know why I am making exercises and why I am insisting on computer codes. You know why. Actually, we don't have much time to focus on the computer code and on computer programming. And I want to give to all of you the opportunity to get to an advanced level of programming. But I need to rush. I need to rush because, you know, we have like 8-10 hours dedicated to exercises. And therefore, if I want to get to a quite evolved level, I need to rush. I don't think it is a big problem because at the exam, as I mentioned to you several times, I'm not asking anything related to programming, anything related to algorithmics, approach, etc. So I don't think you should wonder you should be concerned by the exam. On the other hand, I think that if you want to be able to follow me, you need to do some homework. This is the reason why last week I suggested to you, look at this code before we start, because otherwise it is difficult during the lectures to keep the pace. So this is the reason why I get your question. I am insisting on trying to have a look. So next Thursday, we will move forward with this code, and in 2 hours we will get it done, together with some attempts of finding the best parameter set. So we will move forward very quickly. If you want to take this opportunity with the full immersion, you need, I think, to make some homework. Otherwise, you just have to be patient with me and don't blame me too much if I go fast. Your question?
Are the exercises graded?
No, they are not graded at all. And this is what I specified. And if you look at my first lecture in the website, there is clearly explained. They are not graded at all.
Just to explore things widely.
Yes, yes. And you may decide, as I said, also not to attend these lectures. I tell you, on Thursday, I will make some consideration of theory for about 20 minutes to complete the picture of groundwater flow equation. And then I will move forward with the exercise. It's not a problem at all. But again, keep in mind that today an engineer should be really able to make progress. Okay, thank you very much. And I think we are done. See you on Thursday. If you have any question, also the students connected remotely, take this opportunity for a couple of minutes.
So, actually,
Thank you, Professor.
Thanks a lot.